Hi guys, welcome back to our digital VLSA channel. In this tutorial, we will see about how to design a comparator. We will see not only a 1-bit comparator, but also we will learn about 2-bit comparator using 1-bit comparator. Moreover, in this design of 2-bit comparator, we use even multiplexes. So let us see how to implement that. At first, what is comparator? Comparator means comparing any two numbers. In our mind, we will get whether greater than or equal or less than. When we compare two numbers, only those three outputs will come to our mind. Whether one number should be greater than other number, or one number should be less than the other number, or one number should be equal to the other number. So in the same way, in digital electronics, comparator means comparing two binary numbers. In other words, we can say like comparing two binary inputs. So let us consider this block as comparator block. We will give two inputs, that is A and B. Let us say 1-bit comparator. First we will design 1-bit comparator. Okay. What are the outputs that will come to our mind? Either greater than, equal to, or less than, right? So first we will think, when A is 1, B is 0, A is greater than B, right? So greater than output becomes 1. These two outputs become 0. This is for the case of A greater than B. Suppose when input is 0 and input at B is 1, then A is less than B. At the time, LT becomes 1 and remaining to become 0. This is for the case of A less than B. And also other case is there when A becomes 1 and also B becomes 1, equal to EQ output become 1 and other two become 0. This is true for two cases, when A equal to 1, B equal to 1, and also when A equal to 0, B equal to 0. EQ becomes 1 here also, and remaining 2, that is GT, LT output becomes 0. So this is about the functionality of a comparator. Let us see what are the equations we get by using truth table. Okay. What we considered before, A, B are inputs and GT equal to and LT are outputs, right? So how many combinations we get? 2 square equal to 2 square equal to 4 combinations we get. So A0 0 0 1 1 0 1 1. For A is 0, B 0, EQ become 1, remaining to become 0. For A0, B1, LT become 1, remaining to become 0. For A1, B0, GT become 1 and remaining to are 0. For A1 and also B1, EQ become 1 and remaining to are 0. So these are the outputs. What are the outputs? GT, EQ, LT, right? So now we need to write how equations for GT, EQ and LT. For GT, when A equal to 1, B equal to 0, GT become 1. Only that is the case. So GT becomes A into B bar. Why B bar? When B is 0, it is becoming 1. For EQ, in two cases it is becoming 1. For A0, B0 and for A1, B1. So A bar, B bar plus AB. What is this? This is XOR. A X nor B. We can write like this, right? A bar B bar is for this case when A0 B0. AB is for this case when A1 B1. Yeah, this is for EQ. And for LT, only when A0 B1 LT become 1. So A bar B. So here I will write clearly what is the equation of GT A B bar. What is the equation for EQ A X nor B? Sorry. A A X nor B. What is the equation for LT A A bar B? So these are the equations. Just I am writing for reference. EQ equal to A X nor B, LT equal to A bar B. What are the how many inputs? Two inputs. A B. We need A bar, right, for LT, so A bar also I am taking. We need even B bar for GT, so I'm taking B bar also. This is B bar, this is A bar. A B bar AND gate becomes GT, right? A XNOR gate becomes EQ, equality condition. A bar B AND gate becomes LT. So this is the hardware implementation of 1-bit comparator. Okay. Now we need to consider some points here. Before starting 2-bit comparator, let us try to see one example. Suppose in decimals, I am discussing just decimals. A is 56, B is 41. Then which is greater? Blindly we can say A is greater than B, right? By how we are particularly observing tens place. Here 5 is greater than 4. So we are not at all bothering about ones place. So blindly we will say A greater than B. Even in the case of A 51, B 47. Even though in ones place B is greater, but we are seeing only tens place and we are saying A is greater than B. Of course, correct, right? Because 51 is always greater than 47. That means what will be our output? 100. 1 is for GT. So GT became 1 L equal to EQ. This is LT in this case, right? Similarly, when A is 20, in the case of A and B are equal, that is A is 20, B is 20, we get output as 0, 1, 0. That means GT as 0, 1 is for EQ and LT becomes 0. What if in the case that is when both of the digits in tens place are equal? Then we need to go to ones place and we need to check whether the ones place of A is greater than B, or ones place of A is less than B, or ones place of A is equal to B. These conditions when we need to check only when the digits at tens place are equal. Suppose for example, A is 59, B is 50, then by looking at this we can't determine whether A is greater than B or equal to B or less than B. So we need to consider ones place. These are ones place. By looking at this we can say definitely A is greater than B. So output we get as 100. Similarly, let us consider 40 and 42. By looking at this we can say A is less than B. We get output as 001. 1 when what is 1 here? LT becomes 1. It means that 1. What is 1 here? GT become 1 here. Yeah. Why I am telling this means, suppose if you consider AB tens units. First we will look at tens place. At tens place, if A is greater than B, we get blindly output as 100, and these are don't gets. Whatever here is doesn't matter. So we get main output as, let us consider this GT as GT1, G EQ1, LT1. Okay, this output as, this is don't care, right? In this case, when A greater than B case at tens place, yeah, only looking at tens place. Let us consider these outputs as GT2, EQ2, LT2. The main output, we doesn't want this one because we already proved that at tens place A is greater than B. So blindly the main output GT, EQ, LT becomes 100. Is it true? Yes. Now let us consider for A less than B condition. Okay. Particularly we are observing tens place. TU. When we identify, suppose 5, 7, only tens place. 5, 7. We clearly say that A is less than B. Output will become 001. This is don't care, right? The main output also becomes 001. As we discussed this as GT1, this as EQ1, this as LT1. These three as GT2, EQ2, LT2. This is main output GT, this is GT, this is EQ, this is LT, right? Now when tens place and units place, we consider these two places, right? Okay, when the digits at tens place are equal, then we need to concentrate on units place. Then we know the movie. What? If A greater than B, 100 comes. 010 comes when A equal to B at units place. 001 when A is less than B. Why I am saying all this? You will get a question like this, right? Why I am saying all of this means, before we discussed only for one bit comparator. Now if you want to compare um, two inputs, each of which are 3 bits or 2 bits or 4 bits, then how to compare? what process do we need to follow? So what the process we need to follow is the same process what we have discussed before for tens and units place. The same we have to follow in binary numbers also. Okay, let us consider the circuit. That is, suppose this is A, B. A is 2 bit, B is 2 bit, right? What we will get? G, E greater than equal to less than. Suppose um, I am considering A as 1 0, B as 0 1. First we need to see these bits. These are here, 1 is greater than 0. So blindly we can say A is greater than B. So we get output as 1 0 0, right? What if A is 0 0, B is 1 0 or 1 1? Blindly by looking at this, first we need to look the leftmost bits. Blindly we can say A less than B and we get output as 0 0 1. What if A is 1 0, B is 1 1? Now by looking at this we can't determine, can't say. Definitely need to consider this one. So by seeing this, A is less than B. So we will get output as 0 0 1. Suppose let us consider 2-bit comparator. 2-bit comparator. That means A has 2 bits, A1, A0. B has 2 bits, that is B1, B0. First we will look leftmost bits, and then if A1, B1 are equal, then we will look the bits, that is A0 and B0, and then we compare. Now I will design the hardware implementation of these 2-bit comparator, and also I forgot to mention one thing. First we will look at this, right? That means we are comparing this one. So we use here 1-bit comparator, and then to compare these bits we use another 1-bit comparator. To get final output we need to use one combinational circuit here, so that it will give the final output whether it is greater than or equal or less than. I will discuss what is that combinational circuit. Now let us consider A has 2 bits and B has 2 bits. A1, B1 goes to one comparator, that is 1-bit comparator. So which has outputs as G1, E1, L1. What A1, B1, this one is the same A0, B0 go to another comparator, which is 1-bit comparator. Then we get output as Z0, E0, L0, or we can assume anything Z2, E2, L2. It's not a big matter. Now when A1 is greater than B1, we can directly say that main output is 1 0 0. Suppose main output is GEQ, GEL, we can say 1 0 0, right? Now If A1 is less than B1, then also we can directly say without involving this circuit whether it is less than, A less than B, we can directly say that is 0, 0, 1. What if A1 equal to B1? That means this condition become 1. Then we need to look this circuit. The same thing applies here. When A0, B0, if A0 is less than B0, then we get main output as 0, 0, 1. And if A0 is greater than B0, we get 1, 0, 0. And if A0 is equal to B0, we get 0, 1, 0. This is how we get the outputs. Now, what hardware implementation we need to do here to get outputs like this? Now, let us discuss its detailed hardware implementation. See, as we discussed before, we use two 1-bit comparators. That's the thing I am using here. One, it is A1, it is B1, A0, B0. We know what are the outputs we get also. G1, E1, L1, G0, E0, L0. Now, if G1 becomes 1, suppose if A1 is greater than B1, G1 will become 1. Blindly we can say the output, main output GEL or 1, 0, 0, right? So, which gives that? Um, 1 second. Which gives that? The multiplexer gives that. Here I am using 3-bit wide. That means each input of the multiplexer is 3-bit. Let us assume G1 goes to selection line. If G1 is 1, we will get blindly 100. 100 means what? I am writing like this: GT, EQ, LT. We blindly get output as 100. That means greater than becomes 1, EQ becomes 0, LT becomes 0. Oh, shit. Yeah, this is 100. What if G1 is 0 and L1 becomes 1? Now again another multiplexer, and this second select line for the second multiplexer, and if it becomes 1, blindly we can say 001 is the main output. This is when G1 condition fails, and when G1 condition fails and L1 become 1, we get output as 001. This is just 3-bit wide. That's why I am writing here 3. Here also 3, that's why I wrote. Now what if L1 becomes 0? What input should be here? This whole input should be here. That means Z0, E0, L0. According to this, the main output will be printed or will be shown. So this is about 2-bit comparator, and we have seen how to implement 2-bit comparator using 1-bit comparator and 3-bit wide multiplexers. Here 3-bit wide means each input has 3 bits, whereas select line has 1 bit, and also the output has 3 bit. Here GT, EQ, LT, each of these output has 1 bit, and we combined those 3 together so that it formed 3 bits. That's it, guys. If you have any doubts, let me know in the comment section. It's a bit hard, but you can understand it easily. And if you like this video, please share and subscribe to our Digital VLSA channel. Thank you. Bye.